Okay, hello everyone. So this is the first video that I'm posting for our newly started online class. I'm going to start with a couple of videos that should be reminders of the last thing that we saw in class, and because I know that several of you missed those classes, hopefully you'll use them to catch up, and the next week I'm starting with the material that we haven't covered yet in class. So the last thing that we did in class was to start section 4, which was integrals of trigonometric functions. And integrals of trigonometric functions is the last of the sections that we have in chapter 2, which was techniques of integration. So this is the very last thing that is going to be included in your test 2. Okay, so we're going to start with integrals of trigonometric functions, but to do that, we have to go back to calculus 1 and remember what the derivatives of trigonometric functions were, because if we want to integrate, we need to know what the final result is, so what the derivative is. So that means I'm going to start with a little reminder of some of the derivatives that you learned in calculus 1. And we can start with the most basic ones, which are, to start, the derivative of cosine of x. So the derivative of cosine of x is minus sine of x. And then if you want to find the derivative of sine of x, that's going to be cosine of x. So this should be the easiest ones to remember. The difficult part is perhaps to remember that the derivative of cosine has a minus, but that's pretty much it. So basically any function that starts, any trigonometric function that starts with a c has a derivative that begins with a minus, but that's pretty much it. Once you have the derivative of cosine, the derivative of sine, you might have used in calculus 1 a couple of rules in order to find the derivatives of the other trigonometric functions, like, for example, tangent of x. So the derivative of tangent of x is secant squared of x, which is the same as secant of x, the whole thing squared. Right? So that just means whenever I write secant squared of x, so when I put the little square right after the name of the function, that just means that the whole function is being raised to the power of 2. Okay, so derivative of tangent of x is the function secant of x, the whole thing squared. Then I can look at the derivative of secant of x. And the derivative of secant of x is just going to be secant of x times tangent of x. Then you'll have the derivative of cosecant of x. And the derivative of cosecant is very similar to the derivative of secant, except, well, it starts with a c, so I need to put a minus in front. And then instead of secant, it's cosecant. Instead of tangent, it's cotangent. So minus cosecant of x, cotangent of x. And finally, if I want the derivative of cotangent of x, I'm going to have, again, the same thing as for tangent of x, except instead of secant squared, it's going to be cosecant squared. So that means minus cosecant squared of x, which is the same as saying minus cosecant of x, the whole thing squared. So that means I'm first applying cosecant of x, and then I'm squaring that. Now, of course, the minus has to be outside of the square, because otherwise the square would cancel it out. All right, so this tells us what the derivatives, at least of these 6 trigonometric functions, are. And so now what we're going to do is use these in order to find the antiderivatives of this, like each of these right-hand sides, right? Because we know that if we go one way, we're differentiating, but if we're going the other way, we're integrating. And so if we want to find some integrals, then we might as well start from derivatives that we already know. So I'm going to start with a proposition over here, which is integrals of trig functions. And there's we have 6 functions over there, which means we know 6 derivatives. That means we're going to have 6 antiderivatives as well. Okay. So the first thing we're going to do is find the antiderivative of sine of x over here. So that means find the integral of sine of x. And the antiderivative of sine of x is the function that gives me the derivative sine of x, which means it should be cosine of x, but it has to have a minus in front because otherwise my result over here would have a minus, and it doesn't, right? So that means that that minus was canceled, which means that it must have been in the original function. And then I have to have plus c because I don't know if my original function had a constant or not, right? And if it did have a constant, we don't know what its value was. Then, if I want to find the antiderivative of the function cosine of x, same thing. So cosine of x is the derivative over here. So if I want to find the original function, if I want to integrate this, I'm going to get the original function sine of x over here, right? So the function that gives me a derivative that's equal to cosine of x is the function sine of x. And then plus any constant c, because I have no way of knowing what that was. Then, if I look at the right-hand side over here, that means I'm going to say the derivative is secant squared of x. So if the derivative of my function is secant squared of x, then that means that my original function must have been tangent of x plus my constant of integration as well. And then I can keep going like this for the other functions as well. So for example, here I could have integral of secant of x times tangent of x times tangent of x with respect to x. And if the derivative is secant times tangent, then that means that the original function must have been secant. And then plus a constant. And finally, you have the last couple of functions over here, which are cosecant and cotangent. So I'll just complete those derivatives. Okay, so after completing those 2 last integrals, you see the integral of cosecant times cotangent, applied, of course, to the same thing, is going to be minus cosecant of x, and the antiderivative or integral of cosecant squared of x is going to be minus cotangent of x. So I'm just going to do a couple of examples over here for us to practice those integrals. And it's our usual example, so we're going to start with example over here, and then it just means evaluate the following integrals. So the first integral we're going to evaluate is the integral of cosine of 3x with respect to x. And here I want to encourage you to take 2 minutes to try to solve this on your own. And then so just pause the video for 2 minutes, solve this on your own, and then you can play the video again to see the solution. All right, so if you try to evaluate this integral, you'll see that we are trying to evaluate the integral of cosine of something, which means that we should at some point end up using the second property that we have over here. But that something is not just x, which means that we can't just say that the antiderivative of this is going to be just sine of 3x, right? So we can say, like, maybe let's write that. This is not going to be just, the integral of this is not just going to be sine of 3x. Okay. Instead, I'm going to have to do some extra work. So what I can do is, because I know that there's an inside function, then it seems reasonable to try to do a substitution. So that means the inside function over here would be u is equal to 3x, which means that du would be equal to 3 times dx, which would mean that if I want to replace just dx, du over 3 is equal to dx. Now that means is now I can replace 3x with u, I can replace dx with du over 3, and now I have a strategy for everything that's in my integral. That means I'll have integral of cosine of u times du over 3, right? And this is the same as 1/3 times the integral of cosine of u du, which is equal to 1/3 times sine of u, because now I can integrate that piece. Now I just have cosine of a single variable, so sine of u plus c, which means that if I evaluate this, I'm going to get 1 over 3 times sine of, and of course u was just a label for my inside function, which means I'm going to have sine of 3x plus c, which is the same as saying, just another way of writing, sine of 3x over 3 plus c. Right, so we just did a substitution over here, and we found that the antiderivative of cosine of 3x was sine of 3x over 3. Now that's the, the very rigorous but kind of long way. So we did a full substitution in order to go from this place to this place. But we could have done just the same thing if we had realized that this is actually, so 3x, my inside function. So 3x, the inside function, was a linear function. The inside function was linear. And the fact that the inside function is linear means that the derivative of the inside will only be a constant. And that makes it easier to evaluate the integral over here, because if I want to evaluate this integral, I could just say, well, I know that the antiderivative of cosine of something is going to be sine of that same thing. And the derivative of the inside here would have just been 3, right? So that means I would have just had that when I applied chain rule, a 3 would have come out. And so all that I have to do in order to make sure that I get the right derivative is divide by 3 to cancel out that constant that would have come out. So I would have sine of 3x over 3 plus c, and I get exactly the same answer that I got by doing substitution, except it was a lot shorter, right? So the very important part here, though, is that the inside function has to be linear, otherwise this doesn't work. Okay, so let's do another example. We'll have the antiderivative of 4x times secant of x squared times tangent of x squared with respect to x. Okay, so what we have over here is integral of 4x times secant of x squared times tangent of x squared, which means that we have a single function, which is the function, just write that in a different color. This is like the function secant of something times tangent of the same thing. And this function secant times tangent is being applied to the same inside function, which in this case is x squared, which means that if I wanted to do a substitution, this seems like the right choice for my inside function, right? So that means that I should use x squared as my inside function. and then you'll have enough terms over here. So you have the derivative of x squared looks similar to the term that I have at the beginning of my integral over here. So what I'm going to do is use u is equal to x squared, and then see if that helps. So that means that du is going to be equal to 2 times x times dx. And I have 4x over here, which means that I'm going to have enough to replace this and then another 2. So that means if I rewrite my integral, I'm going to get integral of 2 times secant of x squared tangent of x squared. And then I had 2 times x. I'm just putting the 2x next to the dx so that it becomes clear what I need to replace. And so I get integral of 2 times. Now I can replace the x squared by u. So I'll have secant of u times tangent of u. And then the 2x dx is replaced by du. Right, so now if I go back to the derivatives that I have over here, I have that if I want to integrate the function secant times tangent, which is applied to the same variable with respect to that variable, so the function secant times tangent of x, the integral of that is going to be secant of x. So if I want to integrate secant times tangent of u, then I'm going to have that the integral of this is going to be just secant of u. So that means I'm going to get 2 times secant of u plus c. And now I have secant of u. Of course, u is not the original variable that I started with, so I need to back substitute. And I'll get that this is 2 times secant of x squared plus c. All right, so these are two fairly simple examples of evaluating integrals of trigonometric functions. With this, you can start trying at least a couple of the problems that you have in the practice set of integrals of trigonometric functions. In the next video, I'm going to start looking at integrals that might be a little bit more, a little bit trickier to evaluate.